Enthalpy of reaction. So enthalpy of reaction is the change in enthalpy for the reaction at a given temperature and pressure. And I want to remind you that enthalpy in chemistry is something that we can relate to heat, and heat is oftentimes in Q. So you can go ahead and kind of think of enthalpy as a Q value. Now, the equation for this is the delta, and you're going to know that delta means change in. So whenever we have anything that is a delta in front of it, it usually means it's some sort of final minus initial situation. And instead of final minus initial for a reaction, we're instead going to be discussing products minus reactants. And so we are going to do the sum. So again, this squiggly sigma means sum of. So we're going to add up the enthalpies of the products, and then we're going to subtract that from the enthalpy of the reactants, and then we can figure out the heat change of the entire reaction, either exo or endothermic. So we are given these thermochemical equations, and the information that we want to look at when we have them available is the coefficients. And we also want to reference the H value, and there is usually a delta here. So we're going to go ahead and insert that value. So we usually have a delta in front of this. So this reaction provided would release 368.6 kilojoules of heat. Again, this negative is exothermic, so that means it's evolving or releasing heat. Now remember, if you change the coefficients of these, this has a direct change on the delta H. So we'll see that as we kind of go through some examples here. So when we are given the equation S8 plus 8O2 yields 8SO2, we have the amount of heat being released as 9.31 kilojoules per gram. So let's actually go ahead and write that, 9.31 kilojoules per gram. And usually we don't see per gram as a unit, we usually see per mole, but we're actually going to be utilizing that gram in this one. Now we're going to calculate this heat in kilojoules per mole. So we have to use our equation that we're in, or our units that we're trying to get to as kind of an equation. So right now I'm in kilojoules per gram, and I need to be in kilojoules per mole. So the kilojoules can stay, but I need to get rid of the gram on the bottom and make it become a mole. So that's pretty easy. All I have to do is get rid of grams on the bottom. So you can see here the kilojoules per gram. And remember, when it's per gram, it's the same as saying per 1 gram. And then all I have to do is a gram to mole conversion, and you would use 8 sulfurs. So when you add up the molar mass of 8 sulfurs, you get 256.56. And then you can go ahead and cancel out that gram. So the ending unit here would be kilojoules per mole. Okay, so you'd end up multiplying 9.31 times that 256 number, dividing by 1, and you would go ahead and get your value of negative 202.39 times 10 to the third kilojoules per mole. And again, this is the amount of heat released for this whole reaction. Okay. Now, if we have a reaction and we are looking at the delta H values, and we have delta here. Delta just means change in. A lot of times when I transfer this, the delta doesn't transfer over, unfortunately, but you should see that on your side. So you can see by looking at a thermochemical equation if something is exo or endothermic by the sign in front of the delta H. So when you have a negative delta H value, which you can see here, this means this whole reaction shown is exothermic. Remember, exothermic means heat is released. The products have less heat or energy than the reactants. And when you have a positive or no, just something that has no positive in front of it, an assumed positive, that is endothermic, meaning heat is absorbed as the reaction proceeds. Now, how you would write that if you were to put the numbers inside the thermochemical equation is if you see it on the side of the reactants, this is shown as exo because it is being released. It's a product. And if you see it as part of the reactants, and now I did the colors here for you guys to be able to see it a little bit easier, but if it is a reactant, then it is considered endo because you are adding it to the beginning of the reaction. So 2 ways you can try to understand exo and endothermic. You're either given the sign, positive or negative, or it is shown directly in the equation on the side that is the most appropriate. Now, if you have a thermochemical equation and you are changing the coefficients in front of any of the substances. So let's say, I'm going to use the previous one here as an example. Let's say we were to add a 2 in front of any of these. or all of these, or at least let's just say double all of them, then you'd have to do the exact same thing to your delta H. So if I'd multiply everything by 2, I'd have to multiply the delta H by 2 as well. So it must be multiplied by the same factor, and we're going to see that in a couple examples. And if you would flip it, so let's say we'd take this entire reaction shown here, and I'm going to still keep that 2. So 4NO, so the products became the reactants. Let's say we flipped it, then all you would have to do is go ahead and flip the sign of your delta H. So if it's positive, it becomes negative, negative becomes positive, okay? And we can go ahead and use these coefficients in front as quantities of heat. So let's go ahead and try an example of this. So we have a reaction and we have heat being absorbed. So I'm hoping you see that and you say to yourself, this is endothermic, meaning it has a positive delta H. So rewrite this thermochemical equation with the enthalpy incorporated. So because it's endo, it's absorbed, we're going to go ahead and put it in the front of the equation. So 206 kilojoules, and then you can just continue adding whatever else you have to the equation. Okay. So that's a pretty easy one here. And then is it exo or endo? I might have answered that question already. We know it's endo because it is absorbed heat and it is a positive value. All right, so the reaction shown here below, you can see that the value is on the product side. Because it is on the product side, we know that is exothermic. Heat is being evolved or released are the terms we use. All right, so we have the same equation, that S8 and the O2, and what we're trying to do here now is how can we change this reaction so that we only have 1 mole of the sulfur dioxide? So to get 1 mole of this, I have to cut this from an 8 to a 1. So that means I have to do the same thing to all parts of the equation. So I'm just going to make this 1 SO2. So when I divide all of it by 8, okay, I can go ahead and make this, since this is an 8, I'm going to divide it by an 8, it would be just 1 O2. And again, you don't have to put the 1, I'm just showing you. And then this doesn't have anything, so when I divide by 8, it becomes 1/8. All right, 1/8. So I know that's weird. You may have not seen fraction coefficients yet, and I honestly don't teach it all that often because students get confused with fractions, but in this case you sometimes have to use fractions. So because I divided everything by 8, I had to make that one a fraction to stay consistent. So what would we do to the delta H after we have done that? We would do the same thing. We would cut the delta H by an 1/8 as well. So go ahead and get your calculator out. I'm going to take that that negative 2,390 and I'm going to divide that by 8. So my new delta H given, and the sign stays the same because we didn't do anything, is 298.75. Okay, and again, that's kilojoules. So all I did was divide this by 8 as well. So you have to, whatever you do to one part of it, you have to do to all. So we can actually use these reactions in these delta H's to do stoichiometry calculations. So I'm going to go ahead and demonstrate that. So when 75 grams of that SO2 are produced, what quantity of heat is evolved? Remember, that just means released. So to do that, we always, as usual, are going to start with what we're given in the problem. So in this case, we're starting with 75 grams of the SO2. And remember, I always say, when in doubt in chemistry, you can always convert to moles. Okay, so even if you have no idea what to do, your first step is always going to be to convert to moles. So for the SO2, I'm going to go ahead and add up 1 S and 2 O's and get 64.06. And that's SO2. Now this is going to be a new step here for you. So what you do is once you're in moles, you go ahead and cancel your unit. In this case, moles goes on the bottom and kilojoules goes on the top. So this step is new right here. And to do this step, we need to utilize our balanced equation and our delta H. So in the kilojoules spot, we're going to go ahead and just replace and put this in. So I'm actually just going to make this a larger number here. Instead of scientific notation, it's a little bit easier. So all I did was make that negative 2,390. And then now the big step here is where the mole goes, you have to use the coefficient that is in front of the object or the species that you were talking about. So because this is an 8, we go ahead and put that there because this amount of heat is directly related to that coefficient. All right. Now, once I show students this, they start to go a little bit crazy and start to throw the coefficient in front of everything. But I want to remind you, the coefficient never changes for the mole to gram coefficient. It's always 1. The only time we're going to be utilizing this is now a mole to kilojoule conversion. Okay, so let's go ahead and do some of the math for this. And so I'm going to take 75 times negative 2,390 divided by 64.06, get an answer, and divide by 8. Now my answer is going to be, I'm going to go ahead and round this to 3 sig figs, negative 350, I'm going to go ahead and put a decimal point here, kilojoules, because moles canceled out and grams canceled out, and I'm left with just kilojoules, and this is going to be of heat for SO2. Okay? Let's try one more example here. Now we're going to go ahead and do the opposite. Basically, instead of starting with grams, we want to end in mass. Remember, mass is always asking for grams, so let's go ahead and start with what we have. So we have 5,500 kilojoules of energy, and we're trying to find the oxygen. Remember, the oxygen is going to be by itself here. So we're going to go ahead and kind of do the opposite of that last step that we just performed, kilojoules to moles. And remember, the moles gets the value that's in front, the coefficient, and the kilojoules gets whatever is provided here. So negative 2,820, and that's for the O2. Okay, and then we can go ahead and do a moles to grams conversion to finish this off, and there are 2 O's in there. Okay, so to do the math, I'm going to do 5,500 times 6 times 32 divided by negative 2,820. Now, when you get an answer, you are going to get negative 374. Okay, and actually to round this to sig figs, it should be negative 370. Now, you need to ask yourself, does it make sense that I would have a negative mass? It does not. It does not. So you're just going to have to use common sense to say to yourself, okay, I know a negative sign isn't really a negative. It's not below 0. It just means heat is released. But when we're talking in terms of grams, I would not be able to tell somebody to weigh negative 370 grams. So you just have to realize grams can't be negative.